Welcome back. In the previous class, towards the end of the previous class, we started to talk about the role of viscoelasticity and slippage on dewetting of ultra thin films. So we will continue with that, and in this particular class we will discuss in little bit detail without going too much great into the theoretical aspects. We'll talk a little bit about how viscoelasticity and slippage influences dewetting, particularly in morphological aspects. So the things, let's take a quick recap of what we know. We know what is a thin film, we know interfacial interaction, we now know mathematically the condition under which this interfacial interactions or the surface fluctuations or the undulations can grow due to attractive long range van der Waals interaction, which can result in the formation of hole or a spontaneous rupture of a thin film, which is known as the spinodal dewetting. We also understand how the Hamarkar constant essentially influences the possible stability or destabilization. We also have seen subsequent to that the condition or the morphological evolution sequence that is observed experimentally, which is associated with growth of holes and then coalescence of holes, formation of a rim as a hole forms because of the mismatch in the rates at which the polymer is dislodged and it is redistributed to other intact parts. We have also seen the very interesting role of surface tension, which opposes this instability till a hole opens up or till the film ruptures, and then once the film ruptures, surface tension aids the growth of the hole. And finally, the hole growth can have two distinct regimes or mechanisms. One of them is a neat retraction of the three-phase contact line, eventually leading to the formation or the coalescence of the adjacent holes, resulting in which eventually these polymer ribbons break down into isolated droplets, resulting in a final morphology like this. And in contrast, one can also have a rim instability where the growing hole, the contact line of the growing hole or the rim itself becomes unstable and it leaves behind drops like this, and eventually one results to completely random structures. Subsequently, we started to talk about the role of viscoelasticity and interfacial slippage, and we argued that the existence of slippage in a polymer film can be attributed to the adsorbed molecules at the interface. The extent of slippage is typically characterized by a slip length b, which one can correlate to as the ratio of the liquid viscosity and the coefficient of friction. And we have also argued that since with increase in shear strain, the extent of disanglement of the surface adsorbed molecules increase, or they sort of become less entangled, their level of entanglement reduces. This results in reduced interfacial friction and increases the slippage. The other thing we need to understand, a key parameter related to viscoelasticity of a polymer is the reptation time. Which is typically presented by tau rep. Now, I am not giving you or coming into any details of what is viscoelasticity. Please go through standard literature, because this is something you should have read in your fluid dynamics or some course on complex fluids. All you may want to know some critical keywords apart from viscoelasticity. You may want to have a clear idea about what is storage modulus and what is also loss modulus. So, in a viscoelastic film in an instrument called rheometer, you can eventually individually identify these two parameters, which are the storage modulus and the loss modulus, which are sort of gives you an idea about the extent of viscoelasticity, the relative components of viscosity and elasticity, or relative dominance. Of course, one can use a simple Maxwell model right to very complicated models. The easiest way to understand viscoelasticity of a system is to consider still the spring dashpot. The spring stands for the elastic part, the dashpot for the viscous part. Okay, so this, I'm sorry, this is beyond the scope of this particular course to go into the details of viscoelasticity, but all we will pick up is that for a polymer melt, repetition time is a very critical parameter, because when, okay, so we introduce the concept of repetition time. For the reason why it is important is for time, the polymer behaves like a deformable semi-solid. One can argue that at this stage the level of entanglement of the long chain molecules is pretty high. So, it is related to the extent of entanglement also, and for time t greater than tau rep, the response is like that of a liquid. So, the first thing one needs to understand is that the model that we have talked about, the linear stability analysis, where we took the governing equation to be the Navier-Stokes and we have assumed a Newtonian fluid, essentially we were talking of a regime where time was essentially the beyond the repetition time. So, it was the liquid like response that was considered, which is though surprising, but not a very arbitrary assumption, because this remains pretty valid for short chain molecules, which for the polymers which are not very long chain, as well as if your experiment is done at a significantly high temperature. So, let us say for a polymer like polystyrene or PMMA, if the glass transition temperature is say 100 to 105 degree centigrade depending on the molecular weight, and you are doing your dewetting experiment at, let us say, at a temperature close to 150 or 160 degree centigrade, then well, you are in a regime where the response is liquid like. However, if the same experiment, dewetting experiment, is done at a temperature which is very, very close to the glass transition temperature, and that is where people have studied the morphological signatures of viscoelastic dewetting, then the effect of viscoelasticity becomes very, very pronounced. And what we will pick up is the major influence or major signatures viscoelasticity and slippage in dewetting, particularly the morphological signature, I would say. They include firstly, formation of hole without rims in the early stage of dewetting. Variation of dewetting velocity in different stages of hole growth. Formation of highly asymmetric rims. and possible inhibition of dewetting beyond a certain hole radius. Now, let us consider, or let us point out what are the difference these statements have when you are looking at dewetting of a purely viscous film. In a purely viscous film, so we will write the purely viscous case with green. In a purely viscous film, what happens is holes or rims appear concurrently with holes. Dewetting velocity remains constant. Rim's shape is symmetric. We will talk about it in greater detail, and dewetting goes, we have already seen up to, now you also know, droplet formation. Okay. So, these are some of the differences. So, holes without rims, we will find out some of the reasons why it happens. Variation of dewetting velocity, highly asymmetric rims, and possibly inhibition of dewetting beyond certain hole radius. So, what happens is an exponential rate of hole growth is initially given where we will see how it matters, where tau d is given as 0.780 by V star, and V star is given as the ratio of surface tension to viscosity and is known as the capillary velocity. Okay. This is, so in the initial stage you see a power law, you see an exponential growth rate of holes. This is also in contrast simple power law hole growth rate in a purely viscous film. During hole growth, now what happens is, so this is a hole that is growing. So, during hole growth the gain in the interfacial energy due to amplification of the surface undulations results in an elastic deformation at the film surface. So, now you are talking about, this is important. So, you are talking about a viscoelastic film in the early stage. So, T is less than tau rep, which means that the response is pretty much like a semi-solid or a soft elastic film, and therefore, the surface fluctuations which are present on the surface, and we know the reason for that, results in an elastic deformation at the film surface. This results in a Laplace pressure of S by H at the film surface, okay, at the edge of the hole. Okay. Okay. And this causes the elastic stress to propagate across the film at the shear wave velocity as a long range plug flow without any localized accumulation of polymer. Which results in holes without rims. Okay. Here. So, this is important. So, in the early stage, T is less than tau rep. During hole growth, the drain in the interfacial energy due to amplification of the surface undulation result in an elastic deformation at the film surface, and which results in a Laplace pressure at the edge of the hole, and this causes the elastic stress to propagate across the film at the shear wave velocity as a long range plug flow without any localized accumulation of the polymer. So, we get holes without rims. Now, this regime of rim continues as long as interfacial dissipation remains insignificant. Or in other words, what it means, the dissipation is due to viscous dissipation. So, this means the response is predominantly elastic. The rheological response of the film elastic, and which lasts to a stage where the hole radius remains less than delta, where delta is defined as H0 into B, B is the slip length raised to the power half. Okay. As R exceeds delta, interfacial dissipation starts dominating, due to enhanced friction, and as a result the shear stress gets screened at a finite distance. So, earlier what was happening, that the shear stress, elastic shear stress was propagating across the film at the shear wave velocity as a long range plug flow without any localized accumulation. So, which resulted in holes without rims, and now due to enhanced dissipation, due to increased friction, the shear stress gets strained at a finite distance, which results in the appearance of holes, appearance of rims, I am sorry. So, in this regime continues till this the radius remains within this range. So, this is the regime 2. The increase in the capillary driving force which is proportional to the perimeter of the hole gets balanced by an increase interfacial dissipation, and consequently which results in a constant dewetting velocity. So, this is important. In the initial case, we had a dewetting velocity which or the whole growth rate which had an exponential increase, but now in the regime 2 the dewetting velocity becomes constant. Beyond R is greater than B, the regime 3 sets in. What happens is the width of the rim increases now, the width of the rim increases and enhances the interfacial dissipation. Okay. And as a result of which so interfacial dissipation, which was earlier getting balanced with the capillary driving force, now starts dominating. So, as a result of which the dewetting velocity now progressively reduces. Okay. And once the imbalance becomes too high, then dewetting stops completely. Okay. So, these are the three regimes or three distinct regimes one has in dewetting of viscoelastic thin film, so first stage with a rapid hole growth with holes without rims. Second stage, constant dewetting velocity, and appearance of holes, appearance of rims. Third stage, widening of the rims, which leads to increased interfacial friction, and that might reduce or completely stop dewetting. Okay. So, this is the key difference of the key signatures of viscoelastic dewetting. The other important thing is that if the effect of viscoelasticity is too high, this is the typical rim shape. As compared to a much uniform curved shape observed in a purely viscous film. In fact, the rim shape also undergoes a change. With time. So, here no rims, appearance of rims, initially they are highly asymmetric rims, and at the later stage they become much more circular in nature. So, at any intermediate stage, the shape of the gives an idea about the forces dominating the regime. Okay. So, this is, I guess, a reasonably good level of idea about this should be a reasonably good introduction to the effects of viscoelasticity on dewetting, and I don't. So, this is again a very advanced research area where a lot of activities are still going on. But anyone who is interested, you are encouraged to see some of the recent work. So, you can just search the internet with keywords like viscoelastic dewetting. Amongst other things, there was something very, very important and interesting that you might have noted in the context of viscoelastic dewetting, and that is the third stage. Though there is a, so from the standpoint of dewetting dynamics or how the morphologically it evolves, widening of the rim, interfacial friction becoming extremely important, etc., etc. The other important thing was that dewetting completely stops. So, which implies that viscoelasticity imparts at least partial stability to a dewetting film. The other important, very important aspect of research on dewetting is actually to understand the mechanism that leads to this instability and then work out strategies which can suppress dewetting. because this morphological evolution is perfectly fine for understanding the physics, is very rich, but the moment you get omega greater than equal to 0 from your linear stability analysis and the characteristic equation, what it implies that in the first few lectures of this course we had talked that one of the biggest application of thin films lies in coatings and things like that. Okay. So, what needs to be understood that there is a significant level of research activity that is going on at working out strategies which can suppress the dewetting, right. Issues are that when we even when the rooms of your rooms are getting painted, for example, you always tell the painter to apply 2 coats. So, what exactly you do? You essentially, by applying this second coat, you are making the thickness of your film adequately high. So, now you know that if your thickness is high, okay, so then the interfacial interactions, even if the van der Waals, the nature of the interfacial interaction is attractive, since it is in the denominator and with some higher power h square, h4 or whatever, that magnitude will be very, very low. So, implicitly without understanding the essential physics, we have been applying or adopting this approach for a long time now. But what needs to be understand that we have also talked, particularly in the context of lithography or soft lithography, that now there is a tendency or there is a trend of going in for extremely low feature size. So, earlier any coatings people used to make few hundred nanometer to micron thick. So, anyway it would have been stable against any spontaneous instability. But now with extremely low feature sizes, it may not be possible to always work with extremely very high or very high thicknesses. So, one has to essentially now work with films which are very, very thin, and then one has to then talk about, if somebody is working or somebody is talking about a coating application, have to talk about some strategies that can suppress this spontaneous instability. So, work started about roughly 10 years back with one of the pioneering work coming from Professor Alamgir Karim's group. He was then at NIST. So, these are the real top names in the field of thin film instability. We have been citing some of their work. Professor Sharma is at IIT Kanpur. So, that way India has a very strong presence in the international map on dewetting and thin film instability. Of course, we have Ulrich Steiner at Cambridge, University of Freiburg in Germany, University of Akron in USA. So, these are the real top players in this field, and they are all very actively progressing and publishing. So, a lot of new results are coming in. So, about this particular theme of suppression of dewetting, one of the first papers that was published was around 2000, was in 2000, a macromolecules paper, which said that if you add some nanofiller particles to this film, and they added C60 nanoparticles, fullerene nanoparticles, they showed, Professor Karim's group showed that the dewetting gets completely suppressed. So, what was argued? So, essentially what you can see, I got the permission from him to show this image. So, here you have a film which is a polybutadiene film which dewets or ruptures with the formation of holes. You can now understand that this has, the holes have ruptured and it has grown without any rim instability, and the moment you add some nanoparticles of this C60 variety fullerene nanoparticles, the dewetting is completely suppressed. So, what was argued that these particles actually, what happens is these particles, though they are added into the polymer, these particles phase segregate onto the surface and effectively. So, this is how it starts. So, initially the particles are within the polymer film, and once you heat up the particles, due to their preferential affinity towards the surface, or the particles are such that they do not bind to the polymer molecules, they phase segregate the particles to the surface, and thereby what happens is that there a particle rich layer forms close to the surface, okay, and this layer effectively alters the effective wettability of the surface and thereby imparts stability to this system. So, this was one of the very important findings of research, where people essentially utilize the concept of understanding the spontaneous instability in an ultra thin film and then work out strategies to alter the effective wettability of the surface. So, what it implies that as the particles phase segregated to the interface, the sign of the effective Hamarkar constant changed, and you know that a film can become unstable only when the Hamarkar constant is positive. So, what essentially happens is these particles going to the surface, it changes the effective wettability of the substrate with a associated change in the sign of the Hamarkar constant. So, the system becomes stable. Recently there was another nice article in which people looked at the behavior of the particles. Some gold nanoparticles were added to the dewetting polymer film. Here the interesting aspect was that the particles had preferential affinity towards the polymer. So, unlike the previous case where the particles phase segregated to the surface, here the situation was such that the particles preferred to remain within the polymer matrix, and it was seen that depending on the concentration of the added gold nanoparticles, three distinct regimes were possible. For low concentration, the film dewetted completely. For intermediate concentration, the dewetting was partial, and for high concentration dewetting was completely suppressed. So, what happens was this was a 2010 paper from our group in ACS Nano. It is a top journal in nanotechnology, which sort of broke the mystery or broke the myth that was surrounding this area, that you add very little amount of nanoparticle and immediately the film becomes completely stable. But there were a couple of papers around 2007, 2005 where people argued that, well, we are adding some nanoparticles into a polymer film and then still we are observing that the film is dewetting, it is not getting suppressed. So, there was a controversy that was very active. It was a very recent controversy which was going on, and people wanted to know whether the claim that Karim and his co-workers put in their 2000 macromolecules was right, or there was something more which was not reported. So, indeed in certain cases dewetting was getting suppressed, but in certain cases the film even with the nanoparticles were sort of dewetting. And so, our results, these results show that yes, it is possible, that it is not only a function of whether you add nanoparticles, you need to understand what happens. So, what we could figure out is that of particular interest was the case where one observed partial dewetting. So, what happens is as it has been already pointed out that these particular particles were preferentially stayed within the polymer. So, as the polymer film ruptured and the hole started to grow, the particles also was there within the film, and there was no trace of particle in the ruptured zone of the hole. So, So, this implies that the particles did not go to the interface, as was the situation with the fullerene nanoparticles. So, this was verified, but during the hole growth something very fascinating happened, and this will really fascinate the chemical engineers as a community. So, you have this surface tension driven bulk motion, macroscopic motion of the hole growth. You have seen in some of the videos how the hole grows. So, effectively there is a component of bulk velocity over here, and then what you have here is these particles which is embedded in a matrix of these long chain polymers. So, these smaller particles have much faster rate of diffusion as compared to the bulky polymer molecules. So, this allowed these gold nanoparticles or the nanoparticles to sort of migrate. We are just showing one side of the rim, migrate at a faster rate as compared to the long chain polymer molecules, which also diffuse, as you know that the rim formation itself occurs because there is a mismatch at the rates at which the polymer is dislodged from the surface and gets redistributed to other intact parts of the film. So, what happens is these tiny nanoparticles sort of migrate at a faster rate, and ahead of the rim, just ahead of the rim, forms a particle rich zone. So, though it is argued that initially the particle distribution of the particle was uniform, due to the bulk motion during opening of the particle, there is an in plane phase segregation of the particles. So, here the particle concentration remains unaltered as that of the initial film. But here, because of the faster diffusion, of the particles through the bulky polymer molecules, there is an in plane phase segregation. Okay. And this results in a zone which is richer in particle concentration. Now, the particles have preferential affinity towards the polymer. So, consequently what happens is over this zone the particles sort of act as virtual cross-linking center where many polymer molecules sort of get attached to one of each particle. So, this results in some sort of a virtual cross-linking. And this zone therefore becomes almost elastic and therefore hinders the growth of the holes. So, this is a very exciting result, and this was published in a paper in a journal called ACS Nano in 2010. So, if you are interested in looking at the original manuscript, either you can download it or you can just send me a mail and I will be happy to share the manuscript with you. For higher concentration, what happens is, anyway the particle concentration within the film is high. So, right from the beginning these particles start acting as virtual cross-linking centers. So, effectively imparting some sort of a viscoelasticity or higher level of viscoelasticity or elasticity to the film, and thereby they stabilize the suppression or stabilize the instability. So, this type of work they have extreme industrial application and extreme industrial potential potential for practical application, because these are the type of work that can allow you to make ultra thin coatings thinner than 100 nanometer for various optical applications, various other types of applications, lubrication of MEMS devices and things like that at very small length scale. It might be important where you really do not want your film to sort of become unstable and you want your film to remain stable. So, these can be very nice approaches. The other thing is that since you are talking about addition of nanoparticles, so you can use different particles with different levels of functionalities, and in the process you can make functional coatings. So, where also these coatings can be stable. So, these nanoparticles in that case can impart two roles. One is to bring in the functionality of their own functionalities, as well as those particles can act as stabilizing agents as well. So, a lot of research on these areas are going on. So, this is something what we showed or what we discussed about this particle rich zone, what is happening, and it was verified experimentally with some careful measurements. Another interesting aspect that I will now introduce you, maybe few minutes, is the dewetting of a polymer bilayer. There can be various other critical considerations, but let us try to understand it in terms of van der Waals interaction only. So, what we have understood in the context of a single layer film, that if it's a wetting film, so it's a liquid film coated on a solid surface, there is active interfacial interaction, which can be due to the van der Waals forces. And what happens is that out of these two interfaces, the liquid solid interface, this interface, or let us mark it 2, is sort of a rigid interface. It can't deform because the solid it involves a solid. So, its shape or geometry is defined by the shape of the solid itself. But therefore, if there is an if there is an attractive interfacial interaction, the only deformation is manifested at the liquid air interface. In contrast, if you now have a polymer bilayer, okay, so you have essentially film 1 and let us say film 2. So, which is now coated on the solid surface. Okay. So, what is this case like? It is like you now have, instead of 2, you now have 3 interfaces. One is a liquid air interface, liquid liquid interface, or film air interface, film film interface, and film substrate interface. Now, the interesting thing is that amongst these 3 interfaces, only this one is a rigid interface now. The other 2, both the interfaces, both the liquid liquid and the liquid air interfaces are deformable interfaces. Okay. So, what is the advantage or what is the consequence? Consequence is now depending on which of the interface becomes unstable faster, the overall morphology which of the two interfaces becomes unstable faster. So, if the interfacial attraction between these two interfaces is stronger and sort of this acts faster as compared to the interfacial attraction between these two interfaces, then what is likely to happen? What is likely to happen is this, that because of this interfacial attraction between the film and the film substrate interface, it starts to deform, and since it starts to deform, the other film, the top layer film, also follows it, and one might have a situation where the bottom layer has ruptured, and then there is direct interaction now between the liquid air or the film 1 air interface and the substrate. So, depending on whether this interaction is attractive or repulsive, you can have different regimes. So, if this is repulsive, this layer can also dewett or rupture and can form in a morphology like this, or sorry, if it is attractive. If this interaction now is repulsive, maybe there will be no subsequent evolution. So, you get embedded structures like this. So, this is otherwise difficult to fabricate. The other interesting thing is that we have seen in the relations of lambda and n and all that, also the feature height, it scales as the surface tension is also present there. So, the moment you have a liquid-liquid bilayer, this is now an interface, polymer-polymer interface, and typically interfacial tensions are roughly 1 order lower than surface tension. So, therefore, what happens is in that relation of lambda, n, etc., if you now have the interfacial tension value, the surface tension value gets replaced by the interfacial tension, and which is 1 order smaller. So, lambda, n, etc., they are all going to be reduced. So, you also achieve significant feature dimension miniaturization by using a bilayer. Now, this mode of instability where the deformations are in phase with the deformations of the two layers are in phase with each other, this is what is known as the bending mode of deformation or the zigzag mode of deformation. In contrast, you can have a completely different dewetting scenario if the interaction between this interaction sort of starts dominating, and these two interfaces, the attractive interaction between these two interfaces becomes or sort of makes the top layer film rupture first. And the important thing to notice is that here both the interfaces between which the interaction is going on are deformable interface. So, you can expect to have some sort of a morphology like this with a resultant rupture of the film over here. Now, this is a classic example of a liquid layer now resting in equilibrium with another liquid surface, and unlike the Young's equation or the Young's configuration, what we are more used to seeing on a solid substrate with a liquid, the equilibrium configuration, for a liquid on a liquid, the configuration is known as Newman configuration. Okay. So, it is like this is what is known as the Newman construction, not consideration, it is Newman construction, and so this is a situation where you would essentially get a Newman construction, and depending on whether there is interfacial interaction, active interfacial interaction between these two layers, yes or no, because one of the things can be the bottom layer can be very, very thick. So, in that case the situation becomes like you have only one dewetting layer, that is the top layer, but which rests on a liquid surface instead of a solid surface. So, depending on whether there is repulsive interaction, attractive interaction, so you can get different morphologies. So, one of the important thing is the moment you have a bilayer dewetting, there are various morphological signatures, and I do not think it is important to go into all the details. So, you have liquid 1 and liquid 2. So, suppose if your top layer is sort of dewetting, we know about the formation of these rims. So, one of the critical things that happens is here you are essentially dewetting on a liquid surface. So, what happens is, so this is the bottom layer, there is always a possibility, and this particularly happens if the top layer dewets on an intact bottom layer. So, top layer dewets on an intact bottom layer, and there is a possibility of the rim penetrating into the bottom layer. So, since the rim now gets penetrated into the bottom layer, so the dynamics become sluggish. So, this is just an example of what are the complexities that can arise in dewetting of a bilayer. There can be various examples, various case studies. Simulation results have been just published 2-3 years back. Experiments are still active, and a whole lot of exciting things are happening in this particular area. So, with that I stop my this particular class. In the next class we will take up how template guided self organization or assemblies can be used to guide these random instability structures to make something worthwhile or useful from these patterns. Thank you very much.